Unit 7 is about the attractions between particles. The attractions between particles. Structural particles. Now, yes?
Is there like a lot of equations in this?
Yeah, there's a lot of equations in this one. Yep.
What annotations you got to do tonight?
The rest?
No, you have pages 15 through 27 tonight. The rest is on them.
Wait, like they're due? Those pages are due tomorrow?
Yeah.
I can do that.
Okay.
He told me this morning. I know. We felt like a 2-hour break.
Guys, calm down. Yes, I did tell you, but I also wrote it on the board for you.
Yeah, like I'm aware of what pages are due, right?
Okay.
It was like day after day.
Please be quiet and give me your attention. All right, so yesterday when we did the lab, we looked at how particles were interacting with a surface. All right? The whole idea behind the activity we did in the hallway where we threw plastic balls at a target and measured the force was to look at how pressure results from gas particles, where that force of those particles hitting acted on a surface area. That's what pressure is. By definition, pressure is force acting on an area. Okay? Well, this whole unit is about how particles interact. The second, well, it won't be the second half in terms of the amount of time we spend on it, but the second half of the unit is about the laws that govern gas particle behavior. So we can predict the behavior of gases based on some pretty straightforward gas equations. All right, so that's what you were talking about, Scholar, right? But in terms of the big picture for this whole thing, there are three major factors that impact whether a substance is going to be a solid, liquid, or gas. Now, it actually impacts a lot of other things too, but we're trying to keep it pretty simple in this level of chemistry. So we're just looking here in terms of how it would affect something being a solid, liquid, or gas. And solid, liquid, or gas is all about structure. Okay, so I need you to think, put on your thinking caps, put on your imagination caps, okay, run the little movie in your head, and I want you to think about what the particles are doing as I kind of describe this, okay? And you know this already. This is not a new concept. This is stuff you've had in, I don't know, all the way back to elementary school. Okay, you know that, you know that, guys, can I have your attention, please? You know that when solids form, what are the structural particles doing there?
Slowing down.
They're stuck together. They are slowing down, but they're stuck together. That's how you form a solid. You stick the structural particles together and they don't move around each other. Okay? All right? So you can think about it like you guys sitting in these desks right here. You're stuck together. And you're wiggling around. Okay? Yeah? Okay? You know, Bailey back there is brushing her desk, and Tyler's moving around over there. Everybody's moving around, but nobody's moving in relationship to each other. Okay? So solid structural particles behave that way. They are moving around. They're just not moving around each other. Okay? Yeah. They can wiggle. They can twist. They can vibrate, but they're not moving around each other. All right, does that make sense? All right, everybody know what a mosh pit is?
Yes. Yes.
Mosh pit. What's a mosh pit? All right, listen. Listen, I want you to put your imagination caps on, man. I want you to think about people in a mosh pit. They're pretty much shoulder to shoulder in a mosh pit, aren't they? But are they moving around each other?
Yes.
Yeah, they are. That's a lot like how a liquid structural particles behave. They're touching, and they're wiggling, and they're twisting, and they're vibrating, but they're also moving around each other. So solid particles don't move around each other. They're like students in desks in rows, okay, sort of. But a liquid, the structural particles in a liquid are like people in a mosh pit, okay? They're touching, but they're moving around each other. All right? What now? They are. And okay. All right. So gases. Listen. Listen. Guys, I'm getting frustrated because I'm saying listen. I'm not saying be quiet. I'm saying pay attention over and over again, and I get the feeling that a lot of you aren't. And my job is to teach you, and I can't teach you if you don't pay attention. Okay? So if I have to make you be quiet and not talk at all, that's what I'll do. I'd rather not. Okay? Right, James?
Yes, sir.
All right. So gas particles are different from those because they're not even touching, except when they bang into each other and bounce off. Okay? So you can think about that like bumper cars. Okay? For the most part, they're not touching. But they're banging off each other, moving around, bouncing off the sides and everything, aren't they? Only real gases, the particles are much, much further apart on average than bumper cars are. Does that make sense? Okay? You kind of got the idea in your head? What they behave? Okay. So then, what is it that causes structural particles to go from this organized solid structure to the less organized liquid structure and the even less organized gas structure? That's part of it. That is one of the big factors that affect that. And in your unit handout, you had a Venn diagram like this one that explained all that. Okay, look at the interaction of those different factors. Yes? Okay? So all of these are factors that affect the state of matter. If you're having a conversation that's not about chemistry right now, are you really paying attention? Well, we're not worried about a different kind of chemistry right now. We need to be worried about this kind of chemistry, okay? This is important.
Are we finished with our lab, Mr.
Not entirely, but we're finished with doing the lab. Unless somebody's going to come in and redo their measurements. I think one group was going to come back and redo their measurements because they had a problem with the data points. Okay? So how fast the particles are moving, that's one of those things, right? All right. Now let's be careful about that because we're not talking about them moving in any way at all. This is random motion. That means particles moving in every direction at a whole bunch of different rates of speed, actually. Okay? This is random motion, not just moving in a direct straight line. If all the particles are moving in the same direction, that is not the kind of particle movement we're talking about here. So this is random motion. Okay? And random motion defines temperature. Random motion defines temperature. Okay? So, we're going to introduce to you now a new definition for temperature. A new definition for temperature. We may have mentioned it before, but you're responsible for it in this unit. Temperature is a relative comparison. Temperature is a relative comparison of the average random motion. a relative comparison of the average random motion and mass of the particles in a substance. Random motion and mass of the particles in a substance. If you put motion and mass together, you get something called momentum. Okay? So sometimes you'll hear me say that temperature is a relative comparison of the random momentum of particles, okay? Because it means the same thing. Does that make sense to you? Motion and mass together make up a property in physics and chemistry we call momentum. All right? All right. So one factor that affects the physical state of a matter's physical state, a substance's physical state, is how fast those particles are moving. That's what we talked about. Okay? But what actually gives us the structure is whether those particles are sticking together, okay, in a rigid sort of structure like you sitting in a seat, or whether they're moving around each other like a mosh pit, making a liquid, or they're spread out all over the place like a gas. All right? So how much this random motion impacts that physical state is part of these other two factors as well. And one of them is the strength of attraction between particles. Okay? So particles that have the same random motion, the same momentum, but the strength of attraction is different. One can be a liquid and one can be a solid. One can be a solid or one can be a gas and one can be a liquid. All based on the strength of attraction. A good example is water and methane. Water and methane have about the same mass. Okay? They have about the same mass. But if the temperature is the same, say room temperature, water is going to be a liquid, but methane is going to be a gas. Because water has a much higher strength of attraction between particles. Okay? Does that make sense? All right. Water is a polar molecule, a very highly polar molecule. And so the attraction between one water molecule and the next is really high. Methane's nonpolar. That's CH4, I'm sorry. Okay, methane is CH4. It's a nonpolar molecule. Okay? They weigh about the same. They're about the same size. The real difference between these two is the strength of attraction between particles. Water is a liquid in this room most of the time, but methane is going to be a gas. And it all has to do with the strength of attraction between particles. Okay? So the last factor is the size and shape of the particles. The size and shape of the particles. All right, so we just mentioned methane. It's a gas at room temperature and pressure. But a molecule like this, which is just as nonpolar, would be a liquid at room temperature and pressure because of its size and shape. Okay? So this is a gas at room temperature and pressure. and this is a liquid at room temperature and pressure. All because of the size and shape. The temperature can be the same. The strength of attraction is the same because they're both, well, there's another property we're going to talk about. Has to do with this too, but it affects strength of attraction. But basically, it's the size and shape of the particles that matter. Okay? And then if I get a carbon chain like this, or a hydrocarbon chain like this, that has 20 carbons, hydrocarbon groupings, I'll have asphalt. And that's not a liquid either, that's a solid at room temperature pressure, right? That's the blacktop on the highway. Okay? So the size and shape of the particles make a difference in terms of whether you have a solid, liquid, or gas. Now, to understand this, you've got to be able to kind of imagine what the particles are doing. You've got to be able to sort of run the movie in your head. You've got to think about that. And you can relate these to things that you understand. Things that you have. It's not just tiny, tiny particles, for which there are billions in the tip of my finger here. Okay, that's the size of the particles that makes a huge impact in the overall structure. Okay, you've got to be able to imagine what those particles are doing to understand how this is affecting these things. Okay, I'm going to give you some tools for that to help you, but it's best understood if you can imagine how the particles are interacting with each other. Does that make sense? Now, understanding how the particles are interacting goes back to our concept in Unit 1 of a model. Models in chemistry are attempts to explain behavior, by explaining what you think the cause is. And the cause in chemistry, more often than not, has to do with the way those particles are interacting. Okay? That's a model. You need to know what a model is. Models are a proposal. Models are a proposal that explains the cause of behavior. Models are a proposal that explain the cause of behavior. They have to be scientifically reasonable. And most of the time in chemistry, they're describing how particles interact. Most of the time in chemistry, they're describing how particles interact. Most of the time in chemistry, they're explaining how particles interact. That was a period right there. They have to be scientifically reasonable. And then the last thing was, most of the time in chemistry, they're explaining how particles interact. Uh-oh. Okay. So that's kind of the big picture here of the theory we're going to be dealing with in this unit. Okay? You need to understand, you need to know this. And you have notes now, I hope, and you also have a unit handout with those explanations in it. If you need to go back and study it, go back and study it. Annotations, remember, they're required, but they're tools for studying. They're designed to mentally focus you on the key stuff you should know. Does that make sense? All right.